I'll be talking about stellar evolution today, and I would like to start it off by saying I literally just graduated school, so the amount of stuff I know is very basic. And if you have any questions, I would probably direct it to Samarth because I know he's really into astro, right?
Yeah, cool. You don't worry. Like, it's just a platform. You need not to be like, no one is scientist here. No one is like real astrophysicists. It's just everyone is learning with each other. So it's not
Thanks.
to worry. Okay, just you just be what you want to be.
Thanks. Okay, so Bugs, next slide. So we'll be taking off from where you left off last week. So you left off at where a protostar is formed, right? So from this stage, it can take two parts basically, depending on the mass of the star. So it can either become a brown dwarf or a main sequence star if the mass is less than 0.8 solar masses, then it becomes a brown dwarf. If it's higher, then it becomes a main sequence star. And brown dwarfs are unable to fuse hydrogen, but they are thought to fuse deuterium, although we haven't actually observed it yet. Oops, okay. And they are around 13 Jupiter masses. I have no clue why it is related to the mass of Jupiter, but that is what I found. And main sequence stars, obviously, as we know, it follows the classic hydrogen, deuterium, helium route of fusion. And the larger the stars, the shorter the time it lives on the main sequence itself. This is because it needs to fuse faster and it uses up all of the elements in the core to maintain the equilibrium of the gas forces. So it has a shorter lifespan. Bugs, next slide. And this is the Hertzsprung-Russell diagram, which is basically it's used to find the star's internal structure based on its position in the diagram, which you can determine with its luminosity and the temperature. And the sun is thought to lie somewhere right in the middle of the of the main sequence. So somewhere where the yellow dots, yeah, the yellow stars start, and yeah. So obviously you can see like colder, uh, hotter stars would be. I mean what? Sorry. Hotter, more brighter stars would be on the top left, and like so on based on the diagram itself. Pugs, next slide. Now, main sequence stars, if they are greater than one solar mass, they go through the carbon, nitrogen, oxygen cycle. And they become stable with this really quickly because of the forces from fusion itself. And this counteracts the force from gravity and forms a stable mass. When the hydrogen is depleted, obviously the force produced by fusion is going to be less and than gravity. So it either succumbs to the electron degeneracy pressure, or it starts fusing helium at 100 million Kelvin, whichever comes first. Now, more massive stars have a core temperature of 10 million Kelvin, where they start fusing hydrogen to helium through the proton chain reaction before the electron degeneracy pressure acts on it. And if you are not familiar with the electron degeneracy pressure, it follows after Pauli's exclusion principle and the Heisenberg uncertainty principle, which we discussed on Wednesday, because the electrons are forced into such a small volume because of gravity. And since no two electrons in the same space can have the same spin in the same energy state, obviously, they create a pressure to support the star. And because we know the position of the electron with more certainty, the momentum is large and so it produces a pressure. Bugs, next slide. So now it'll split into three sections, which is basically low mass stars, medium mass stars, and massive stars. So what actually happens when low mass stars cease to fuse uh, hydrogen is unobserved for less than or around 0.1 solar masses. But otherwise, they stay on, like they form red dwarfs and they stay on the main sequence for around 6 to 12 trillion years. And then they form white dwarfs, which also stay around for around hundreds of billions of years, which is why we haven't observed it because it's too long. So all of the hydrogen in the star fuses to form helium, and it doesn't just form a helium core, it forms like the whole star turns into helium. Uh, and so when stars are greater than 0.8 solar masses, they do become red giants and they increase in temperature and luminosity. So they become brighter. I mean, sorry. Yeah, they become brighter. And they don't have a helium core, so there's no helium fusing. And they have a lower luminosity and they eventually turn into white dwarfs. Now, stars larger than this, but which are still classified as low mass stars, don't have a core massive enough for helium fusion itself. Yeah. Books. Next slide. Hi. Sorry, can you all hear me? Can you hear me, guys?
Yeah, we can.
Sorry.
Yeah, we can hear you.
Raining, so my network is doubtful. So in this slide, we can basically see what happens with diffusion itself. Uh, so initially, you can see on the top left that there's a hydrogen core and it's fusing into helium. So this produces an outward force, but also gravity acting inwards. And then eventually, when a helium core is formed, like it's denser than hydrogen, obviously. So there's a shell of hydrogen fusing around it, around the helium core. And because of gravity, the shell is pushed outward and the helium is all pushed inward. And this is what we call a red giant. And the outer layers are obviously cooler than the core itself. Pugs, next slide. And then now we go on to medium mass stars. These are from 0.6 to 10 solar masses, and you'll find them on the top right section of the Hertzsprung-Russell diagram. And they have, when they're on the red giant branch of the diagram, they have a inert helium core and hydrogen shell, and then they progress on to have a active helium core. And when they go into the asymptotic branch, asymptotic giant branch, they have a carbon and helium core with a hydrogen shell that is burning. Now, when the hydrogen core is exhausted, the hydrogen in the shell outside is still burning, so it produces more helium and it expands and cools, but it's less than what would happen in the main sequence itself. And the temperature of the shell increases as well as the luminosity, and then it follows on to the red giant branch of stars. Pugs, next slide. Now, after this phase, it follows on to the subgiant phase, where all of the hydrogen in the core is exhausted and it fuses to form helium. So the core is increased in mass and these can last anywhere between millions to 2 billion years. And at this point, the core is degenerate when it's around one solar mass, or if it's greater than that, then it forms an opaque core. Now, what a degenerate core means is that it is either under the electron degeneracy or neutron degeneracy or whatever force is applicable at that stage. And the fermions are pushed so close that they basically can't exist due to the exclusion principles. Now, both of these, either if the core is degenerate or the opaque layers, can cause the hydrogen shell to again increase in temperature and luminosity. Pugs, next slide. Now, after this, we go on to the red giant branch phase. At this stage, the outer layers become convective, which means that the fusion products in the core become available to the surface for the first time in the star's lifespan, unless it's a very small star. And this is called a dredge up. So what the effects of this you will have is lower carbon 12 and carbon 13 ratios and altered carbon nitrogen proportions. So after this, the helium core grows in size because of more fusion, and it either becomes degenerate or it reaches the Schoenberg Chandrasekhar limit, which I'm not sure how to say the first guy's name, but basically the limit means that it's the maximum mass that a non-fusing isothermal core can support an enclosing envelope, and the ratio is in it's a ratio of the mass of the core to the total mass of the star. And after this, it increases in luminosity and reaches the tip of the red giant branch in the Hertzsprung-Russell diagram, which we can get back to at the end if you guys need to. And all of the stars, regardless of their mass, at the end of the red giant branch phase, they reach a similar endpoint in terms of the mass of the core and the luminosity, except for the more massive ones, which are able to fuse helium much before that. Pugs, next slide. And then we go on to the horizontal branch. This is where the core is around 0.6 to 2 solar masses, and it's supported by electron degeneracy pressure, and it goes through a helium flash, which is basically a brief thermal runaway for nuclear fusion of helium to carbon by the triple alpha process. But if the core is more massive, then the helium is ignited slowly without a flash. Oh, and also the helium flash releases a lot of energy, which is around 10 to the power 8 of the luminosity of the sun for a couple of days. Or for a couple of seconds, it actually releases more energy than approximately the brightness of the Milky Way galaxy itself. But this energy is consumed by the thermal expansion of the star itself, and so it's not really visible outside or to our telescopes and stuff. Uh, Now the star contracts and it migrates on the HR diagram, and it also increases in surface temperature. And the hydrogen fusion and the total energy release of the star decreases after this stage, after the helium flashes occur. Next slide. And then we move on to the asymptotic giant branch phase, where this is basically after the consumption of the helium core. So it forms a carbon and oxygen core instead, and the hydrogen and helium fusion is in shells around the core. And At this point in its life, hydrogen fusion produces more energy than helium. But because of this, there's obviously more helium being produced in the outer shells, and this causes a thermal pulse, which is when the helium from the outer shells is dropped into the core because of gravity. And this causes the energy output of the helium core to increase dramatically up to hundreds of times because of this at intermittence, and this can happen like even up to hundreds of times in the star's life. And this dredge up also causes carbon stars to be formed, which is when obviously it has a carbon core. And these are cooler reddened stars when you see them. And they also have strong carbon lines in their spectra. Sometimes you may have hot bottom burning, which is basically carbon turning into nitrogen or oxygen. This may occur before the second dredge up, and this will determine its luminosity and its spectral lines. But for the more massive stars, they become more luminous and the pulsation period is longer, causing more mass loss, so it's not very visible at visible wavelengths. And they have an oxygen-rich core as well. Pugs, next slide. Now, after this phase, it's pretty much the end of a medium star's lifespan, a medium-sized star's lifespan, because they run out of fuel for the shell to burn, and there's not enough. It's not large enough for carbon fusion either. So it contracts further to form a planetary nebula, which is basically just gas rich in all of the fusion products, but particularly oxygen or carbon, depending on the star itself and what uh, it fused to form. The central star is still there, and it cools to become a white dwarf, and it forms a circumstellar envelope on the outside. That is all of the cloud that you see around it. This is basically a roughly spherical cloud that you can see, which is not gravitationally bound, but it's actually formed by dense stellar winds. And you also have post AGB thermal pulses as well. They don't just occur in the asymptotic-giant-branch phase. These pulses, uh, they also cause it to produce stars which aren't very well understood at the moment. They're called born again AGB stars because we really don't know how they work. Bugs, next slide. So this is basically wrapping up the medium-sized stars lifespan. As you can see, the sun in the middle of the main sequence, a bit off the middle, and you can trace its path through the red giant branch after the helium flash. And yes, thank you, books. Do you guys need some time to see it, or can we move? If you guys want to speak or text in the channel, either way is fine. Okay, I guess we should move on to the next slide then. Books?
Yeah, you know.
Okay. So for more, for this is now the third classification of stars, right? This is massive stars that are more than 9 solar masses. Uh, when they expand and cool, they don't brighten like low mass stars, and they have a large core because they ignite helium before the electron degeneracy pressure acts on them. And they also form highly luminous supergiants. But after this, if the core becomes large enough, then they can collapse into neutron stars or black holes. Books, next slide. Uh, Now, before the core gets large enough, goes through a phase called the supergiant evolution, where they're around greater than 40 solar masses. So it goes. Uh, okay. So the stars have rapid stellar winds, which basically rip off the gas surrounding it, so they never become red giants, and they retain the blue-white color from the main sequence onwards, because when they leave the main sequence. And this can also happen with small stars in binary systems, which are never able to become red giants because the companion star strips off the envelope as it expands, or they can rotate rapidly enough so that the convection extends from the core to the surface, and this means that there is no separate core and no envelope, so they can't become red giants either. I hope I'm not going too fast. I tend to do that when I'm nervous. And when the helium fusion finishes, you are left with a carbon and oxygen core. And the carbon further fuses by the alpha process as well to form neon, sodium, and magnesium. But the less massive stars, they form an oxygen, neon, magnesium white dwarf. Books next slide. So the maximum limit for carbon burning is around 8 to 9 solar masses, and it leaves a core of around 2.5 solar masses. And sometimes neon can burn before oxygen, and it causes the formation of around 8 to 12 solar mass core, which is unstable, and it eventually forms an electron capture supernova. Now, the change from carbon to an iron core can take hundreds of years, and this is, of course, I'm talking about iron 56 or sometimes nickel 56 as well. And this goes on until they reach the effective Chandrasekhar mass, which is actually different from the actual Chandrasekhar mass. It can range from around 1.34 to 1.8 solar masses, depending on the metallicity of the star and a lot of other things, the temperature and size of its core. So then electrons are captured because of them reaching the limit, and they can either form a supernova or a black hole depending on its mass. Books, next slide. So when the core collapses, it has two paths it can take. It can either form a neutron star or it can form a black hole. And and it forms a black hole when it exceeds the Tolman-Oppenheimer-Volkoff limit. And some of this energy is released in the form of a supernova, which we can observe with a surge of neutrinos being produced, right? This energy from the neutrinos which are released is used to fragment nucleons, and it causes a shock wave, which is due to the rebound of the material from the collapse of the core, which then causes electron capture of additional electron capturing, which then causes additional neutrinos to be captured. And then, because we know that only elements only up to iron 56 can be formed in the core of the star, so everything beyond that, up to uranium or sometimes even more, are formed in supernovae. Oops, next slide. Okay, so that's pretty much the end, wrapping it all up. You can see like the path of low mass stars and high mass stars as they go through their life cycle. And that's pretty much it. Does anyone